This is podcast number 58, and today we're looking at the aerodynamics of trees. And you might be thinking, why do we care about the aerodynamics of trees? One of the main reasons is because wind is one of the causes, or the main causes, of tree failure. So when they break, and obviously we don't want trees breaking and falling onto things. So it's interesting to know the aerodynamics. And to look at this, we're looking at a paper called Wind Loading on Scaled Down Fractal Tree Models of Major Urban Tree Species in Singapore. It's open access. You can find a link in the description. And it was aptly published in a journal called Forests. Okay, so let's get into it. So they say wind is one of the major causes of tree failure and is essential to accurately understand the wind loads affecting individual trees during risk assessment, so see if they're going to break. In simulations, the tree is usually modeled as a momentum sink. So that's interesting. Instead of having the actual geometry in the CFD model, a lot of the time they just put it as a momentum sink, and usually I would imagine they'd put it more as like several momentum sinks instead of one momentum sink. And the momentum sink is just you can think of it as an introduction of a different like it changes the force artificially. It's not due to geometric, it's just due to a mathematical term in there. And they say it is difficult to prescribe the drag coefficient correctly with this approach, though. One of the most detailed numerical simulations of a single tree was conducted using RANs. This study used a discretized momentum sink to simulate the wind drag on a tree, and the drag coefficient was tuned until the simulation outcome matched the experimental measurements. So what that means is they know that it's dodgy, but they manipulate things until they finally do get something that matches what they hope to get. So say the method, while effective, still requires multiple simulations to determine the proper drag coefficient. The authors also observed that the drag coefficient is highly dependent on how well the tree model is described, and hence it is difficult to compare the drag coefficients of different studies, depending on the model that you're using in your study. It could be different between research groups or even between different campaigns that you have. They say one of the major challenges in constructing tree models is to resemble real trees. They constructed tree models on 7 major urban tree species in Singapore based on statistical data gathered through laser scanning of real trees. And that's interesting. We'll get into this laser scanning in a bit. So they say the main aims of this study are to devise a wind load simulation methodology that works on trees, to validate the simulation methodology using experiments, and to collect species-specific bulk drag coefficients. So they want to just look at all these different tree species and see what the drag coefficient of them in general is on average and the spread. Furthermore, the non-flexible tree models and the usage of a wind tunnel reduces uncertainties in the experiments so that the simulation can be properly validated. So that's interesting. In real life, trees obviously flex, and that's going to change aerodynamics. One limitation in research is what they're saying here, in wind tunnels usually don't have flexible trees, which helps validate CFD, but that means it's not really as applicable to real life as if you did have flexible tree models. The tests also provide reference bulk drag coefficients important for practical use for a quick tree failure assessment in the field, especially for trees with weakened trunks that are more vulnerable to low wind speeds. So onto the modeling of the trees and making them. So they wanted to make these tree models, and as you can imagine, trees are quite complex. They have a lot of different limbs. To get around that, they're using 3D printing. They're using selective laser sintering, which is where you shine a laser into your cube of material, and then you cure the material at that point, and then you move along, and then bit by bit you build your model. They said the material of choice was nylon, and the models were all built at 200 millimeters in height. At 200 mils, though, the Reynolds number of the wind tunnel tests are significantly lower than the Reynolds numbers of the real trees, but the eventual bulk drag coefficients measured in the wind tunnel are within reasonable range compared to real trees at low wind speeds. So the Reynolds number similarity is there to an extent, like you're in the same sort of regime. I'm guessing that because trees are fairly porous and there's a lot of sticks sticking out, they make the flow very turbulent. So that means that you don't really have to worry about the transition regime too much, because that's probably going to be at a very low Reynolds number, and you can get into the turbulent range quite easily at a very low Reynolds number, at a very low velocity as well. And then they have some pictures of these trees. They're really cool how they made them. They're a bit difficult to describe, so I'm going to try to describe a few of them, but if you want to see what they look like, these 7 different species, just to click the link in the description to go to the paper and you'll be able to download it for free and see it. But anyway, for models A and E, they kind of look like Christmas trees. Like if you think about the Christmas tree, how they just have these little sticks coming off in this kind of shape. That's what they look like. Figure G, that looks like a willow tree, how it's very bulky underneath. And then F, that looks like a juvenile, like a baby eucalyptus tree. I know that most people who are listening to this are not going to know what that looks like, but that's the only tree I really know that it looks like. The other 3, I don't know how to tell. Like one of them looks almost like a snowflake, figure D. But yeah, so download this paper just to see these figures, or you can see it on our YouTube channel. The the names of these trees I haven't actually tried to pronounce in real life yet. I thought I'd save the first try for this tape recording. That way you'll maybe get a fun thing to listen to. So tree A is called the Kea senegalesis. Tree B is Hopia odorata. Tree C is Samanian saman. Tree D is Sweetenia macrophylla. Tree E is Syzygium grande. And tree F is Tabebuia rosea. Oh no, sorry. And then tree tree G is Peltophorum pterocarpum. Okay, so those are the 7 different ones in Latin. The tree models development was divided into 2 phases. So the first phase was they did the tree trunks and the branches. Then the second phase is the tree crown, so effectively like the foliage bit where the leaves generally are. Now, interestingly, they say they generated the fractal tree models using procedural modeling based on specific species growth processes and statistical data gathered through laser scanning of the trees. So in other words, each species grows differently, and then they modeled their trees based on this growth pattern. That's amazing. They also say that they used laser scanning, as we mentioned earlier. I don't know if you've ever tried to scan anything with a laser and get like a 3D model out of it. It's really difficult. Like if you have a very simple object like a sphere or something, that's not too bad. Once you start getting complex, you start getting patches in the laser, especially when you have lots of tiny little corners and that, because the laser won't get in too well, and you start getting like little gaps in your model. So to do this for a tree, that's pretty amazing because I have all these branches and that to get a good CAD model. The cleaning time on that would have been horrendous, I think. So they say this is a well-established fractal mechanism in botany and used to generate the tree species models based on the set of rules and parameters which mimic the growth and transformation of living cells. The growth rules were constructed specifically to match the tree architecture of a target species, and the rules dictate the tree growth from a seed into different stages. That's amazing that you can like mimic how a tree grows based on a species from a seed. The result of this process is an average tree model consisting of the trunk and the branches that can represent the target tree species. So that's another thing, like when you're modeling your tree, as we mentioned earlier, depending on the tree that you have, you can have the exact same species, but if one research group is using one particular type of tree, another one is using a different one, you're going to get different results. Here they talk about an average tree. Even then, I'm not sure how average it is. It's based on a mathematical equation, which means you're going to get a repeatable result, but whether that represents the average tree or not, I'm not too sure. But it's good that they have some sort of standard to follow. They say it's important that this approach is adopted to use average representative species models rather than any individual tree reconstructed directly from laser scanning. A laser scan of an individual tree is often prone to acquisition noise, as I mentioned earlier, leaves or epiphytes, all of which conceal the actual branching structure of the tree. So as I mentioned earlier, the acquisition noise, just because, I mean, I haven't done scanning for about 2 years now, maybe, but I don't know how much it's improved since then. And this paper was actually done around the same time that I was last doing scanning. And even back then, you were going to get patches in your model. So they've said it here as well, they were getting patches. That's why they went down to branches with a thickness of greater than 2 mm diameters, because otherwise it was too difficult for fabrication. I'm guessing also too difficult for scanning. So now they go on to the development of the tree crowns. That was the branches and the trunks. Now onto the actual foliage area. And it's interesting how they approach this. Due to the impracticality of fabricating the scaled-down leaves, the tree crowns were represented by a porous volume constructed using randomized tetrahedral elements. Instead of arbitrarily modeling the shape of the crown, we chose to define the crown volume using ellipsoids centered at the tips of the branches such that the resultant crown shape is similar to the target species. So let's talk about this. Instead of modeling each leaf, because when you go to 3D printing, especially on a scaled down version, 200 mm high tree, these leaves are going to be tiny. And I'm not sure what printer they used, but it may not have been possible to print all these tiny leaves as well. They may have been too small, and maybe the quality was low as well, and also become delicate. So instead, and also when you put a load on it as well, they might just break off, like from Aerodynamics. So instead, they made just a general structure with a porosity to it, and they sort of said, okay, this is generally what the whole tree will look like. So they went from a macroscopic level instead of a microscopic level, and to model it. That's an interesting idea. They say that they generated the tree crown to have the frontal optical porosity close to real trees. So the frontal optical porosity was calculated after the crown was merged with the trunk and branches. The process was repeated with incremental changes of the average dimensions of the tetrahedral elements until the frontal optical porosity matched the real trees. So what they're saying is they had an initial model, and then they looked at what the porosity was. Then they tried to match that with real life trees by increasing or decreasing the porosity after that. And the optical porosity is, I'm not too sure because they go into it a bit later where they compare optical porosity compared to aerodynamic porosity. And it's about a 3-to-1 ratio in terms of the aerodynamic porosity is about 3 times greater than the optical porosity. I'm not sure what the difference is. I think the optical porosity is, if you know, let me know. But what I think it is, it's optical porosity is the projection of the 3D object onto a 2D surface and seeing how much porosity there is from there. Whereas the aerodynamic porosity is a volume-based porosity. So the optical porosity is more like a 2D-based porosity, whereas the aerodynamic porosity is more like a 3D-based porosity. That's what I think, from what I can tell. And the optical porosities of these real trees are quite high. I mean, they range, they're about 10% to 20%. So it's fairly high, you'd imagine, considering trees, like if you go and see what a tree looks like, you can actually see quite a bit through it still. And with their wind tunnels measurements, they just use their wind tunnel, which had a contraction ratio of 12-to-1. I just highlighted that because it is fairly good. I mean, anything above about 8-to-1 is very good. It means you need to have a very big area to house this wind tunnel, but you get a very good quality flow out of it. And we've done podcasts on wind tunnels in like the podcasts around the 30 mark, podcast 30, 31, something like that. We did quite a lot of wind tunnel podcasts. If you want to check them out to learn more about wind tunnel design and build. So let's get into the results now. So they used PIV and load cells and LDA in that to wake survey their trees. And they have one figure here, figure 9. They take from the flow field. The velocity deficit can be clearly seen. They extracted all their PIV data and then they plotted onto this graph here. And what they have is just the tree in the middle of the graph and then upstream and downstream of it. And they normalize the velocity to the free stream velocity, which is 5 meters per second. And this is for the Senegalesis tree. And interestingly, they say it's for 0-degree rotation. And this is important because it means that when you rotate the tree, it obviously has a different geometry that's facing upstream, and it's a slightly different geometry that the flow sees. But they go into it later, how that affects the drag coefficient. So that's important to keep note of the rotation of the actual tree. Now this figure here shows that, as you'd expect, the central trunk itself is not that draggy. I mean, it's a central cylinder effectively, but it's once you start getting into the actual foliage, then you start getting a lot of drag, and the wake is the worst at about the mid way level from the trunk, so about 50% up the tree for this particular tree here, and then it gets better. But interestingly, no flow accelerates past the free stream velocity, so everything is below 5 meters per second. And as you go, and I have figures here that show the wake development downstream. Interestingly, they have one wake which is cut straight through the middle of the tree, so 50% way through the tree. And the wake shape has already started to take form. It's already at this circular pattern. However, the wake is not too bad compared to downstream. If you go straight after the tree, the wake is now very wakey. Like there are some regions where the flow is almost 0 meter per second. Whereas when you're halfway through the tree, most of the flow is well above 0.6 meters per second. So it seems like there's quite a bit more deficit coming from the second half of the tree. I don't know. That may be just a qualitative conclusion. And as you go downstream, the wake, as you would expect, becomes more diffuse and starts losing some of its detail as it diffuses. And then they have the average horizontal velocity profile, and they're comparing their experiments with their CFD, and it matches fairly well. So as you'd expect, about halfway up the tree, that's when you get the greatest deficit in velocity. Then it sort of pans out on either side and tends towards no deficit. Near the trunk, there's almost no deficit as well. It's like about a 10% deficit near the trunk instead of at the midsection of the tree. It's like 95%. And then they have their simulated wake, and it matches very closely their PIV. The only problem is that it uses a different color map, so it's difficult to compare them exactly. But generally speaking, they look very similar. They should use the same color map here. They go on and say Figure 13 shows a comparison between the velocity profiles obtained from PIV and LES simulations. It is observed that the velocity profiles measured at different wind speeds are almost identical. This implies that the test case is insensitive to the wind speeds, similar to the observations on inflexible trees in earlier studies. So in other words, the velocity deficits as you change the wind speeds for different trees and at different rotations are not really affected. They all seem to be fairly similar. So that's interesting to note. So as I mentioned earlier, the rotation of the tree could make a difference, but they're showing here that, okay, it's not making a difference for these trees at least. So that's one variable that you don't really need to keep track of much anymore, it seems. Now, moving on, the drag forces. This is quite interesting. They have the measured drag, let's say, of the trees, and they plotted them with the optical porosity. They say measuring the drag from minus 90 degrees to 90-degree rotation angles at every 5-degree intervals is plotted. The bulk drag coefficients are plotted against the frontal optical porosity. The spread of the drag coefficient for natural trees can range from 0.25 to 1.25. And that's really interesting when you think about it. Like, first of all, having a drag coefficient of 1.25 is huge. Like, if you were to try to make an object with a drag coefficient of 1.25, you'd be fairly hard pressed. I mean, if you just get a cylinder or a square or like a cube, it's not that high. So to get 1.25 is very high. On the other hand, to get a drag coefficient of 0.25 is very good, because if you think about even like cars, most cars are not that good. They're usually around 0.3 or maybe 0.27. So to get a tree with a drag coefficient of 0.25 is remarkable, especially considering that a tree is designed to get as much energy as possible from the sun. So take up as much volume and as much surface area as possible, so it can get as much light onto its leaves, and yet it's still getting such a low drag coefficient in some cases. But generally speaking, for most of the trees that they've tested in this paper, they range between about 0.7 and 0.8 for a drag coefficient. Some of them a little bit lower, some a bit higher. And this drag coefficient is fairly independent of velocity. And it's also fairly independent of optical porosity as well, it seems, for these particular cases. They say the bulk drag coefficients measured in this study range between 0.674 and 0.863, which is within the range of the values in tables 4, which gives other values from previous studies. We'll get into them in a second. They say, however, it is worth noting that the trees modeled in this study were modeled based on mature trees. Hence, the comparison of the bulk drag coefficients and the saplings or small trees must be interpreted with reservations. So these values that they have in table 4, which are from previous studies, are for saplings and young trees. So they have hardwood saplings and conifer saplings. They get very similar drag coefficients, but I imagine that it would be a little bit different once they start growing, because small trees typically are less leafy. They're usually more woody, and they have a lot more branches. I know that's my observation of trees. I haven't done too much research into trees, but that's that's what I think. They say the drag coefficients of one of the trees, T. rosea, seem to increase mildly with the frontal optical porosity for optical porosities less than 0.09. Sorry. After that, the coefficients for all tree models generally decrease with frontal optical porosity. So what they're saying is up to an optical porosity of 0.09, this particular tree was seeing an increase in drag. After that, all the trees would reduce in drag with more optical porosity. They say frontal optical porosity is known to be an important factor in the study of a wind load on windbreaking, and the drag coefficient was observed to increase with porosity and peaked at aerodynamic porosities of 0.3 before it starts to decrease. This is what I mentioned earlier, whether the aerodynamic porosity is different to the optical porosity. They don't go too much into this paper what the difference is, but from what I can glean, the aerodynamic porosity is based on a volume, whereas the optical porosity is based on a projection, a 2D projection. They say that value, the 0.3 value for aerodynamic porosity, is called the critical aerodynamic porosity, as explained by Manikathan. Flow goes around the tree and recirculates behind the tree if the porosity is below the critical value, so 0.3. Above this critical value, air goes primarily through the porous tree crown, so that changes the flow physics. There's actually another instance, not for trees, but for swimming, where something similar can happen. So when you're doing freestyle swimming, the best way to actually drag your hand through the water is not to have your fingers completely closed. You should have them slightly open. The reason why is because each finger, between your fingers, you'll start to get a boundary layer forming. And the boundary layer, if you think about it, is slow moving flow. So you're actually creating more drag by slightly putting your fingers apart and creating more boundary layers. And you can actually increase the amount of drag that you have, which is how you develop thrust when you think about it, and you can go faster. It's not exactly the same idea here, but it's a similar sort of idea where the flow physics does change based on the opening of your hand or the porosity of your tree. I just sort of put two and two together. Now they say the optical porosity of 0.09 is equivalent to the aerodynamic porosity of 0.38. And they have, so that's close to the critical porosity of 0.3, which is why after that, all the trees got better with drag. And I have a quick equation here which shows that the aerodynamic porosity is equal to the frontal optical porosity to the power of 0.04, sorry. 0.4, yeah, that's right. So the models are not made to be symmetrical. Hence, as the models rotate, both the porosity and shape change. However, so they plotted the bulk drag against the aerodynamic porosity of the trees, and they showed that as the porosity increases, the drag reduces slightly. However, based on the symmetry, let's go back to the symmetry idea. We saw earlier that even rotating the trees, though, even though it has a different shape that's seen the wind, overall, the drag coefficient was still very similar. So it shows that even though the trees are not symmetrical, the asymmetry doesn't really affect the drag too much on average. Obviously, there will be some trees that grow very asymmetrically, and that will affect the drag. But if the tree is growing somewhat symmetrically with a few different branches here and there, these results indicated that that's not going to make much of a difference. And what's more, if you have a more sticky tree, so if you have a deciduous tree and it's now fall or autumn, that's going to have a lower drag coefficient than if it was in spring when you have a lot of new leaves. So finally, they say, based on this observation, it is evident that the crown shape is also an important parameter that dictates the drag coefficient, and its effect could be more dominant than frontal optical porosity. The tree crowns on broad-leaved trees are often complex, but they are less studied compared to conifers. So that's in this podcast. Make sure to like and subscribe. Let me know what you think about trees and their drag as well. And check out the Atmosphere Hawk. It's an instrument that we make to make your experiments much easier. Most aerodynamicists do not measure the drag of the air that they're in the wind tunnels. And the density of air changes by about 2 to 4% on a regular day. The Atmosphere Hawk measures the density of air for you and gives you a very accurate result. That way you can get rid of that error and find more results. It's much easier for your experiments. So there's a link in the description for it. Check that out. And I'll see you next podcast. Peace out, amigos.